Okay, so let me give you a couple of problems for practice. Let's see here. So practice. Yeah, so the first one, first three is, find derivative. Using the definition. Okay, so the definition, I'm talking about this, right? So limit, so f prime of x, right? It's limit with h approaching 0, and this definition. F of x plus h minus f of x over h. Okay, so here are the problems. So the first one is f of x equals 3x plus 2. The second one, f of x equals 7. And the third one is f of x equals 1 over x squared. Okay, so that these are problems where you just need to find the derivative. And the last one is find the slope. Find the slope of a line tangent to the graph of f of x equals x squared at the point 3, 9. All right, so you can use either of those two definitions. Maybe the one with c is easier, is better. And let me give you the solutions. So the first one is 3, second one is 0, third one is negative 2 over x cubed, and this one is 6. Okay. Yeah, so a couple more examples. So let's start with some function with absolute values. So example 3. So let f of x equal x minus 2. So check if f is differentiable at 2, at x equals 2. Okay, so when we are given a specific number, specific point, I think that definition with c is maybe a little bit more efficient, faster. I don't know. Let's see. Let me write it for you. So f prime of x right, so we have the limit with x approaching c, right? And the formula went like this: f of x minus f of c divided by x minus c. Okay, so we know what c is, right? So c was 2. So if c is 2, it's pretty easy to calculate f of c, right? We just plug it into the function. F of x was absolute value of x minus 2. We double check, yeah. Alright, so we just take that, right, take that c and plug it in for x. Alright, so if we do that, f of c is 0. Okay, so let's try to calculate that limit. So that's going to be limit with x approaches 2, and we have f of x, right? So x minus 2. It should be absolute value. Right, so what I'm doing, I'm just using this definition, right? So f of x is this, and now I'm doing minus f of c, right? F of c was 0, so minus 0. And then the bottom is x minus 2. Right, c is equal to 2. X minus 2. Okay, so yeah, we've done an example like this before. It was a little different, right? This was absolute value of x over x, right? With x approaching 0. Anyway, so this one looks like that. So x minus 2 and x minus 2. All right, so in this case, we need to do, right? We need to look at the limit with x approaching 2 from the left and from the right. So x minus 2 over x minus 2. Okay, so let's see. Right, so we can plug a couple numbers. Say we could plug 1.5, right? 1.5. Let's write those. So 1.5. We could plug 1.99. Right, etc., etc. Some numbers that are close to 2, but from the left. Right, so if we do that, we get if we plug in that first x. Right, so I'm getting on the top. I'm getting positive 0.5. Right, so we could write it. Why not? So it's absolute value of negative 0.5. Okay, and at the bottom we just have negative 0.5. Okay, so you see what's happening, right? So the top is positive, the bottom is negative, the numbers are the same. So that's going to be negative 1, right? That limit. All right, so if I plug in that 1.99, right, I'm getting negative or positive, right? On the top I will get, let me actually write it. So what I mean, okay, let me write those results. Okay, so absolute value of a negative number is just a positive number, 0.5, negative 0.5. So the answer is negative 1. Okay, and then the other one, that's a limit with x is approaching 2 from the right, right, of that x minus 2, x minus 2. And yeah, the numbers we can plug in, right, are, I don't know, maybe 2.5, 2.001, etc. Right, so we'll get, if we do that, right, let's write it. So the top will be 2.5, sorry, 0.5. And I plug in that first, that 2.5, right, positive. And the bottom is also going to be 0.5. And that thing will happen with all the numbers that we plug in, right? We're going to get the same value on the top and the bottom. So this is 1. So you see that right, if I take a limit of x approaching 2 from the left and from the right. The limits are different, right? -1, +1. So the limit doesn't exist. So limit doesn't exist. So the conclusion is there is no derivative. So the function is not differentiable or no derivative. Okay, so that's our conclusion. All right, so I have a couple more examples of some weirdnesses. So this is example 4. And yeah, again, right? So we have a function, so f of x equals x to 1/3. Right, and the question is, does the function have derivative at the origin? Okay, so again, right, we're given a specific set of coordinates, specific x. So I'll use that that formula with C, and yeah, it looks something like this. Limit with x. I don't know. Let me write it. Right, f of c, or f of x actually, minus f of c, and the bottom is x minus c. Okay, so I hope you know that x to 1/3 is the same as cubic root of x, right? Okay, but we're not going to use that radical form. We'll use that fraction form. Anyway, so f of x is x to 1/3. Right, minus f of c, which is 0, right? I get it from here. Okay, you plug in 0, you get 0. Cube root of 0 is 0. And then the bottom is x minus c, so x minus 0. Okay. All right, so what do we get? We have that limit x approaching 0. And we have on the top, right, we have x to 1/3. And the bottom is x. I'm going to write x to the first power. Okay, so the point being, this is 1, by the way. Right, to simplify this, right, this expression, we subtract the exponents, right? So it's going to be x to 1/3, the minus 1. Okay, so 1/3 minus 1 is negative 2/3. Okay, so we found right, that, I mean, we still are doing the limit, right? So limit x approaching 0, and so this is actually, I do need that fraction line, right? Because this negative, right, makes the whole expression go to the denominator, right? So this is 1 over x to 2/3. Right, so that's an exponent. I know it doesn't look like 1. Let me fix it. Okay, so we have x, and then the exponent is 2/3. Maybe I write it this way. Okay, so yeah, we can plug some numbers, right? And if you do that, you'll see that this the denominator, right? So yeah, you can plug a couple numbers, use a calculator, and plug in numbers that are close to 0, like say 0.001, etc. From left or right, doesn't matter. Anyway, so if you do that, you'll see that this will be getting smaller and smaller the closer you get to 0. So 1 over a small number is big number, right? So those numbers actually will be getting bigger and bigger, greater and greater. So what we will get is infinity. And yeah, let's keep in mind that that means the limit doesn't exist. So the conclusion, no derivative. No derivative. And yeah, let's look at the graph. Like, why is there no derivative? Okay, so here's the graph of that cube root of x. Right, so it's supposed to go through the origin. Well, it doesn't, but anyway, so what is happening? So this is f of x equals cube root of x, or 1/3, x to 1/3. Yeah, so if you zoomed in, right, if we graph it on some device and you would zoom in, you would see that at the origin, that line, right, the graph actually is vertical, right? So you know that the vertical line, the slope is undefined, so the line doesn't have slope, right? If we had the tangent line to the graph at the origin, it would be a vertical line, right? The vertical line doesn't have a slope, so slope is undefined. Okay, so that's that. Let me write a little note. So note. So if a function is differentiable at some number at some point, that means that it's continuous at that point. So if a function is differentiable at c, at x equals c, then that means it's continuous. At c, or at x equals c. So yeah, unfortunately the converse doesn't work. So what is a converse? Converse doesn't work. Something's wrong with that word. Let me write it again. I think that's the right way. It doesn't work. So that means, yeah, the function is continuous, doesn't mean that it's differentiable. So if continuous, well, let me write it this way, hold on. Continuous, not necessarily. And that says differentiable. Yeah, so let me give you an example of that. So example 5. And yeah, let's just graph couple functions. So we have graph y equals x squared plus 1, and the other one y equals absolute value of x plus 1. Okay, so let's make those two graphs. That's better. Okay, so let's make maybe this one green. So x squared plus 1, right? So it's just a basic parabola shifted up by 1. And the other one, I'll make it red. Okay, so this is red. The second one is absolute value. So, right, that v shifted up by 1 as well. So now, what we want to do is check if those functions are differentiable at 1. Right? So, not at 1, at 0. So check at 0. Right? So if you zoomed in, right? If you zoomed in at this point, at 0, 1, right? You would see that the parabola, so that's green, so that's gonna be a straight line, right? So at 0, that the slope, right, the derivative is going to be 0. But now if you look at the absolute value and you zoom in, you'll still have that v, right? So now, and you see that at this point, right, at the tip of that v, right, there is no, you cannot figure out what the slope is right there, right? There's no really slope, right, because you need, and you cannot find the tangent line, right, to a point, right? The tangent line needs to be to a curve. So the conclusion is that that the first function will be differentiable, right, at 0, but the second one will not be differentiable. Right, so it kind of illustrates what we said over here. Right? So that second function, the absolute value, right, even though it's continuous everywhere, right, continuous at that particular point, there is no derivative. All right. Okay, so a couple other problems and examples. So example 6. Let's see. Example 6. And yeah, it goes, so given a graph of a function, graph of a function, graph the derivative. All right. So here is the graph of the function. Okay, so it looks something like this. I made it worse. And yeah, so you guys see that right? Remember that we don't really know what the equation of this is, but it looks like it's y equals x, right? So the slope is, that could be 1. So if this is, right, so I'm not saying that this is the equation of that line, right? But we could assume it is. I'm just assuming it is just because it's easier for me to explain what's going on. Anyway, so if this is 1, 2, 1, and 2, right? So now, basically what we need to do is figure out the slope of that line, and then, yeah, derivative is a slope, so, yeah, if it's y equals x, the slope is 1. So what I'm graphing is y equals 1. Okay. Yeah, so that's how you can think about it. So that was, I'm not sure, example 6. So now example 7. And this time I'm given the, so graph of the derivative is given. Derivative is given. Graph the original function. Okay, so let's try it. Alright, so this is like the reversed problem. Alright, so let's say this is 1, 2. Okay, so this time this is the graph of derivative. Alright, so I'm going to write y prime, right, derivative equals -2. So now equation of the original function, right, needs to have a slope of -2. Right, so we could graph something like this. That would work. But we don't know what the x-intercept, what the y-intercept is, or x-intercept. So this could be, right, so I'm going to write y equals -2 x, right? And then plus, right, there's many different options, right? So we could, let me make it dashed. Right, so this line would also work, right? Has the slope of -2. Right, or this one. Right, so we don't know what that y-intercept here is. But yeah, so these are kind of, right, so there is infinite number of possibilities, right, for that function, for the function that has a slope of -2. Okay, so that's it about that derivative. Yeah, until the next time.